Okay, part 3. So, recap. In the first part of the video, we rearranged the algebra, so we were told that it was of this form, and then we used logs to put it into this form. That was the thing we plotted. In the second video, what we did is we used Excel or its equivalents to work out this thing here. Now, what we need to do is compare them. So if we look across this, the gradient of this one was log A. That was the m, that's the thing you multiply by the variable. Well, the gradient of this one is minus 0.0327. Let's put those things equal to each other. So log A equals negative 0.0327. Now, just as a reminder, this log here, really, it's base 10. Using this log, we want to work out what A is. Well, we can rearrange it. This is saying, what power do we have to take 10 to? 0.0327 to get to A. Well, this is the thing that we're going to be typing in. Typing into our calculators, we can use 10 to the power of. I'll just do it off screen. Okay, I've got that number there. So, we've worked out what A is. A equals 0.927. We're just writing it to three significant figures. Okay, but we can do something very similar for working out what K is. Do it in a different colour. If we work out the y-intercept, on this equation here it was log K. On this equation here it was 1.98. So we can do almost the same thing again. So we get log base 10 of K equals 1.98. So decimal point in there. So again, rearranging, we get K equals 10 to the power of 1.98. Now, if it was 10 to the power of 2, we know what it was. It would be 100. So we were expecting something just less than that. Typing into the calculator, it was just less than 100. It was about 95.5. So we can put it all back together. We know what K is, we know what A is, we can put them both into that equation up there. So let's just do it on a separate sheet. Putting it all together, we get that big T equals K, which was 95.5, multiplied by A, which is 0.927, to the power of small t. Common mistake here is people trying to multiply those numbers together. You can't. This one's to the power of t, this one isn't, and so we can't merge them. This here is your equation that we can use. Now, if you wanted to answer questions like, what's the temperature at a particular time, you could put the value of t for time in there and work it out on the calculator to get the temperature. If you wanted to go back again, if I gave you a particular temperature and we wanted to know what time it was for, you could put values in for big T and then rearrange. You'd have to use logs to find small t. I'm just going to do the last part of the question. What's the long-term behaviour of the temperature? If you put a really big number in for t, small t, so let's try, say, putting in 10,000. If you type it into the calculator, well, 0.927 to the power of something really big is smaller than 1. This thing here is going to go smaller and smaller. So the long-term behaviour of all of this should go down to 0 degrees C. Now, this is not the best model for a cup of coffee because we'd expect it to go down to room temperature. So what this is suggesting is perhaps the room temperature of this cup of coffee is in a room that is 0 degrees C, which seems unlikely. Right, I'm going to give you a question to do from the book. On my website, it will be there.